In this video, we're going to do an example of an exponential probability distribution. We're told that a light bulb has an average lifetime of 1,200 hours. We're told that it's reasonable to model the probability distribution of the lifetimes of these light bulbs using an exponential distribution. We're going to use this model to find the probability that the bulb fails within the first 300 hours, the probability that it lasts more than 1,000 hours, and then the median lifetime of the bulbs. So for an exponential density function, remember that we use the mean of the distribution, which in this case is 1,200. We put that as a 1 over the mean in front and an e to the negative x over the mean in the exponent. So our probability density function, or our PDF here, is 1 over 1,200 e to the negative x over 1,200. Since we want the probability that the bulb fails in the first 300 hours, we want the probability that x is less than 300. So we'll integrate from 0 to 300. Antiderivative here will be a negative e to the negative x over 1,200. Plug in your endpoints and you'll get 1 minus e to the negative 1/4, which is about 0.22. For part B, we want the probability that the bulb burns for more than 1,000 hours. So we want the probability that x is greater than 1,000. Well, we could set this up as the integral from 1,000 to infinity and integrate the PDF. However, that's an improper integral, which requires me to take a limit, and I'd rather avoid that if I can. So let's switch the problem around and say that, well, if I want the probability that x is greater than 1,000, that's the same thing as 1 minus the probability that x is less than 1,000. And I don't need to worry about equal signs here because we're doing a continuous distribution. The probability that your x is actually equal to a specific number is 0. So I set up our probability that x is less than 1,000, just like what we did in part A, just changing that upper limit of integration. So our work is exactly the same, except that here at this step, we'll plug in 1,000 for x, rather than when we plugged in 300 for x. So when we evaluate just the integral part, we get 1 minus e to the minus 5/6. But also remember there's a 1 minus out in front, so we just get an e to the negative 5/6, which is approximately 0.4346. Finally, the problem asks us to find the median. That means we need to find the value that splits the distribution in half. So we need to know the value from 0 to infinity where we split the distribution exactly in half, or have a probability of equal to 0.5 of being below that number and a probability of being 0.5 of being above that number. I don't know what that number is, so I'll call it m. So we'll set the integral from 0 to m of our PDF equal to 0.5. We've already integrated that thing twice now, so we should recognize what the antiderivative is. Plug in our endpoints, we should get 1 minus e to the negative m over 1,200. That needs to equal 0.5. Rearrange to get e to the minus m over 1,200 equals 0.5. Take the natural log of both sides. Multiply both sides by negative 1,200 and move that negative up as an exponent. So I can rewrite that as natural log of 2 rather than negative natural log of 1/2. Simplify that number and we get 831.7766.